So yesterday we started with problem number 1. And so today we're going to do problems number 2, 3, and 4. Okay. I'm going to switch to the other side. And on my chart, I'm going to put my graphs down here. So you guys can flip back and forth if you'd like. So one of our graphs is going to be position versus time. One of our graphs is going to be velocity versus time with up is positive, down and negative, and the line is 0. And the next one is going to be acceleration versus time with positive, 0, negative. So that's the same. Okay, so now what we need to do first is draw a motion map on the ramp for the motion of the ball as it goes up the ramp. So we start with a big velocity, and then as we move up the ramp, our velocity should get smaller. So that means that our dots are going to get closer together. We don't want to make them too close together, though, because when we get up on this flat part, then we have to maintain that velocity. And so they have to stay the same distance apart. So I'm going to actually not do too many dots on here. What? Wow. That's weird. Okay. Hold on, I know how to fix that. It does this thing where it extends my display sometimes. And it's just, I feel like every single day, like I redo all these settings and then overnight they all just reset to a default. And then I come in and I expect them to be what I set them at yesterday, but I have to go through and redo them. So I apologize for that. Yeah, keep the changes. Keep them forever. Sorry, I'm going to be sarcastic with my computer now because it's not doing what I want it to do. Forever. Keep the changes forever. Okay, so my what I was saying is that I'm going to start with a positive velocity. It's a velocity that's greater than 0. And so when I roll up the ramp, my ball is going to slow down, which means my dots have to be closer and closer together as I go up. But I don't want to make them really close together because then drawing this will become tedious. So I'm only going to draw a couple of dots going up the ramp. And they're going to get closer to each other. See, it's tricky. I always end up stuck in this hole where they're really close together. And then up at the top, they need to maintain about the same distance apart from each other as they go across there. And so with my motion map, I'm showing that at the bottom of the ramp, it gets a push or something, and it moves fast, and then it slows down as it gets up to the top of the ramp, and then maintains its speed as it goes across. Anybody do like skateboarding? No? Okay. So this is the kind of thing that's actually pretty easy to visualize if you watch people who are doing skateboarding on ramps. There we go. There's my motion map. Bloop, 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 bloop. How'd you guys do on the motion map part? Okay? Yeah. All right. So for position versus time, it does give us one location. It gives us a location at 25 meters, right? We get one at 25 and one at the end, which is 50. And so for the first 25, we have an object that moves the most at the beginning and then slows down at the end. So I'm gonna draw a few dots, like hash marks across here, just so that I know where that is. Because what's gonna happen is my object is gonna start out moving pretty quickly, and then it's gonna slow down. So just like my dots got closer together here, there's going to be less change in the y direction, in the vertical axis on my graph. And so when I actually draw that, I'm going to end up with a slight curve. And then once I hit 25, that's where my velocity becomes constant. And so that constant velocity is going to mean that I have a line that basically kind of kicks out at this angle. Whatever my slope is here, you guys can hardly see this. Whatever my slope is when I hit 25 centimeters is what it's going to continue to be until I hit 50. So it's illustrating that if I were to draw dots for each of my locations, that the vertical change on my graph here would be the same as I go all the way up there. So if I were to look at sort of this triangle, that the height would be the same for each of those. You guys have any questions about the position versus time graph? No. Okay. So for velocity versus time, remember that we can do velocity as the change in x over the change in position over the change in time. And so that's the slope of our x versus our position versus time graph. And so if I look at this, my slope here is constant, right? So I've got a constant positive slope here. Down here, it's not constant. It is positive, but it starts big and then gets smaller. So here we've got a bigger slope. Towards the end, we have a smaller slope. Smaller slope. And then this is the same as the smaller slope. Wrote it really tiny, sorry. So we've got a bigger slope, a smaller slope. Over here, it's the same as the smaller slope, and it's always positive. So, you guys see that? And so if it's always positive, when we go to draw our velocity versus time graph, we're always going to stay in the positive part of our velocity versus time graph. We're going to start big and go smaller and then stay smaller. So we're going to start bigger. Oh, there's another thing I need to show you guys. The point in time where that changes is the point in time when it reaches 25 centimeters. So I'm going to draw some hash marks vertically here so that I keep track of where that point in time is across my graphs. That's just for keeping it consistent. So I'm going to start big positive, and I'm going to go to smaller positive. And then I'm going to draw a straight line across there. So my velocity starts bigger and then decreases, but doesn't go all the way to 0. And then my velocity stays constant as I move across the graph. You guys have questions about that one? All right, acceleration, and that's the new part for us. So we know that our acceleration is going to be our change in velocity divided by our change in time. So it's going to be the slope of our velocity versus time graph. So if we look at our slope here, this is a negative slope. So the slope is negative, and it's not constant. No, wait, it is constant. Sorry. Whew. I do it too sometimes when I get used to these again. This down here, what's the slope in the second part? If the velocity doesn't change, what's the acceleration? It's 0, right? So here our acceleration is 0. So if we go down to our acceleration chart, everything down here, 0. I know my line isn't straight. I just drew it on top of my line. Your line is so wavy, Doctor. I'm so sorry. And then for our acceleration, we've got a negative and constant. There's no numbers here. So we just have to draw in the negative space on the graph a straight line, or at least the best that we can. Guys, if it looks pretty straight, I'm going to assume it's straight, by the way. I'll just give you the benefit of the doubt on that one, because you guys can see the quality of my straight lines. You guys have any questions about number 2? Should I go faster or slower? Same speed? Same speed. Okay. This one, I'll tell you what, personally, I don't like this question. It makes me feel uncomfortable because the ball's going in opposite direction of my graph. I don't know if you guys picked up on that. But I leave it in there kind of because it makes me feel uncomfortable because it's going the opposite direction and I have to think about it. All right, so I'm going to go, I have a ball and it's going to go down a ramp. My ramp changes at 25 centimeters. So whatever I'm doing up here is going to be a little bit different than what's going on down here, but what's happening generally is it's going to speed up. I know I see some of you guys like side-eyeing the windows. It looks really pretty outside. Because it's like the trees are lit up, but it's like a dark sky. Anyway. I watched a documentary about Bob Ross last week. It was like an hour long. I don't know how I got sucked into it, but it was fascinating. You guys know who Bob Ross is, right? Happy Little Trees. Okay, so he's made thousands of paintings and nobody really owns any of them because they just kept them all at the studio. And so now there's an organization called like the Bob Ross Foundation, and they own all these paintings, and they're like, we don't really know what to do with them. Like, we catalog them, but like we've never really considered selling one. Like, dude. For the interviews, they like go in, and it's like all decorated with Bob Ross paintings, which is like really trippy because it's all just like really basic landscapes. Anyway, all right. So when I draw my ball going down the ramp, it's gonna start out. They're gonna start out at a modest velocity, and then I'm gonna spread them out as I go. But if I like go too crazy, I'm only gonna have like one dot down here. So I'm gonna try to not speed it up too much. What I'm trying to do is just draw them so that they're a little bit farther apart with each dot. You can imagine something going down a ramp with a strobe. That'd be exciting. I'm just doing my best here. There, it looks okay. There's my point where my velocity changes. I'm gonna draw my arrows. Gosh, I totally forgot to put my time marks on my last one, didn't I? My arrow should get a little bit longer. Okay, so my position versus time graph. I'm going to have a change that happens about here. This is tricky because I know that the shape that I should get for my position versus time graph is basically a curve. But I have to do this weird thing where I have a curve and then I have another curve, right? But this is like too much of a jump. So, I'm going to hurt myself thinking about this probably. But generally I should have something that's like, oh, this is the wrong curve. It's going to be like this, right? Because it's increasing in speed. So when I think about my triangles, I need the vertical part of my triangle to get taller each time and not shorter. This would be slowing down. This is speeding up. So I'm gonna have a curve. I'm gonna be nice about my curve because I don't want it to be too straight. So there's my first curve for my first part. And then I need to make this part, if I kept going with that curve, it would look kind of like this. But I need it to be steeper than that. That's why I don't like to draw this one, guys. So I'm going to try to make something that gets steeper faster. That looks like a roller coaster I would not want to ride. But I'm trying. Okay. So that's where it changes steepness. So this is going to be an important point in time. So I'm going to draw some dots here to keep track of that part of, or that point in time. All right. So if we go back to our slopometer, remember? We start with a small velocity, and then we increase faster. So what that means is if we start with a small velocity and get bigger, we're going to start with a velocity at 0, and then it's going to increase through time. Then what happens? What happens after we reach our 25 centimeter point? What was that? Yeah, and it's going to increase at a faster rate. So that means that my velocity versus time graph is going to have an even steeper line to it. You guys see that? I made it so that it's a constant velocity, and then my new change in velocity, my new slope for my velocity versus timeline is greater. Because after it gets steeper, this is going to change. Then to do my acceleration versus time, I don't have anything that's 0. I don't have a constant velocity. Both of these are positive, and both of them are constant. But the second one is larger than the first one. So when I draw my acceleration versus time, I'm going to have one that's positive and smaller than the next one because I have a step up in my acceleration. You guys have questions about that one? Okay, so do the last one. Okay, so for the next one, we need to draw a motion map as it rolls up and back down. Yeah, so I'm gonna give myself a graph that I can do here. Position and time, velocity and time. Minus 0 plus 0 plus. Okay, so I made my graphs, my stack of graphs there. This guy, okay. What happens when you push a ball up a ramp and it goes up, it comes back down? Is it slower at the top or faster at the top? I'm not trying to trick you. Well, when it comes back down, it's faster. But what about when it goes up?
Oh, slower.
It's going to be slow at the top, right? So I'm going to have dots that are pretty spread out. I'm going to try to make this easy on myself. Spread out dots. Make it closer together as you get up towards the top. And then it's going to come back down. Look at this. I'm just going to draw. It's not really flying through the air, but it's a motion map, so I can draw it that way if I want to. Okay, so first we're going this way. Our motion is up, 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 up. And then it reaches a turnaround point, and then it comes back down. Kudos to you guys that made it all the way up the ramp. I did not push hard enough. There we go. All right, do you guys see how the arrows start out short, tall, and then they get shorter, and then short and get taller? You remember how I told you before that could tell you about how high to make this go? You know, it was kind of related to how high I was going here. So when we draw our position versus time graph, I'm gonna mark 25 here. Bloop, 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 bloop. You guys ready for this? This is the shape that you should have gotten. It goes up and it slows down and then speeds up as it comes back down the other way. What do you guys think? How'd you guys do on that? Up here is the point where our velocity is 0. That's important. If we see on a position versus time graph that our object changes direction, it has to at some point in there have a velocity that's equal to 0 because our slope is equal to 0 there. Okay, so what does that mean? If I take a look at my graphs, that's an important point because I can mark that. So I'm gonna make one of my hash lines that goes all the way down here so I can keep track of when I have things that are equal time. There, there, there. You guys ready? Ready for this? This is big. All right, so I know my velocity is 0 there. So I can come straight down here, put a point here. What's my velocity on this side? Is it positive or negative or 0? Positive, right? Is it big positive or little positive? Compared to this. This is going to be a more positive slope than this number is, right? So over here, I'm going to have big positive. Then I'm going to have 0, and then I'm going to come this way. As I come towards the end, am I positive, negative, or 0? I heard it somewhere. This is negative, right? And if I did a better job of sketching this and we had actual data, we would see that at the end, the magnitude here is the same as the magnitude here. It's just different in sign. So I'm going to try to come up with a similar distance from 0 and put that on my other end. So it turns out that your velocity versus time graph has a constant negative slope. And in the first half, it has a positive value. And in the second half, it has a negative value. So over here is when you have a velocity that's going in the positive direction. In the second half, we have a velocity that's in the negative direction, right? Because that's all the sign is telling us is which direction it's going. Then, if we want to figure out what our acceleration is, we need to remember, okay, well, our acceleration is the slope of our velocity versus time graph. It's the way that our velocity changes with time. Do you guys see how our velocity versus time graph has a constant slope? Even though for part of it, it has positive values and part of it has negative values. But the slope is constant. Is the slope positive or negative, guys? I thought I heard it somewhere. Negative, yeah. So we've got a constant negative slope here. So when we go to our acceleration graph, we're going to just draw a straight line somewhere in the negative half of our graph. So we don't have values for this one. So now we have a constant acceleration down there. What questions do you guys have about number 4? Okay. So we've got enough time left, I think, that we can go ahead and do a little bit of work on the next problem set. You guys ready? Maybe. Look at this. It's just called stacks of graphs. This is one of my favorites. Let's see. I'm not expecting us to finish it, and I'm not going to sign it for homework because tomorrow's Halloween, and I genuinely hope that you maintain your childhood so far and go trick-or-treating if you can. Right? Okay. Go trick-or-treating. That's your homework. Okay. Safely. Wear a mask. Okay. So in order to do this, we're just going to do the same thing that we've been doing. By the way, this number 2 is a typo. It should be over here. All right, so all you need to do for these guys, you're going to be given one of the representations of motion that we have. So let me see. You guys with me still? You guys are going to be given the position versus time graph. And using that information, you need to create a velocity versus time graph, an acceleration versus time graph, a motion map, and a description. But check this out. There's a space here for a velocity motion map and an acceleration motion map. Velocity one is the one that we normally do. Acceleration is kind of a new idea. All right. So I'll show you guys how I approach these. Let's see if it helps you. I take a look at the position versus time graph, and the first thing that I do is to figure out velocity versus time. I'm going to say, okay, is my slope constant, and is it positive, negative, or 0? And so when I look at this, I see a constant slope. It's constant, and it's positive. The one on the other side is constant and negative. And this one is bigger than this one. So when I come down to the velocity versus time graph, that's not straight at all. My first line is going to be positive, constant, but not really large because I need this one to be bigger. And I'm going to go farther away from the axis to draw the second line. And then this line, so that's what I put in that. So this line here is constant going across there, and it is in my, let's see, there's my change in velocity is 0. Here my change in velocity is 0, which means, because they're horizontal lines, it means that in each of those I have 0 acceleration. I know some of you are like, how can you have no acceleration if you change speed? I'm just going to leave a tiny gap there, right? Because something happened. Something happened there. For my motion map, I start at a position away from 0, and I move in the positive direction at some speed for a couple of seconds. It doesn't really tell me how many. And then I'm going to come back the other way at a faster speed. So I'm going to cover more distance for each dot, and I'm going to go past my first one. And I have different length arrows there, right? That corresponds to the positions that I would have here. Just trying to eyeball my dots, right? So those dots kind of go with those dots. The length of my arrows kind of correspond to these heights. And then for my acceleration map, what I'm going to do is draw this with my dots in pretty much the same spots. And we're going to take a look at what's happening here. Do I have any acceleration for any of those? If I don't have any acceleration, I'm not going to draw no lengths. Wow, I'm not going to draw any lengths. And I was recording that, guys. So the only place there could possibly be some is over here. But we're not going to worry about that right now. So then our description, and this is like what we did last unit. Object starts at a positive position. Moves in the positive direction. Turns around and moves at a greater speed in the negative direction. And then stops. I'm going to put behind, but in quotes. Stops behind starting point. What questions do you guys have about those? It's all stuff that we've done before. It's just a little bit more practice at